In this video, we're going to discuss the general shape of polynomial functions. So in previous units, we've talked about degree 0, degree 1, degree 2, degree 3, degree 4, and degree 5. This is what those look like when you graph them. So when we have a degree of 0, that's a constant, and that's always going to be a horizontal line. Now, it could be at any number. This one just happens to be at a positive number. But this is the general shape of what a constant function looks like. When you have a linear function, that is when it is of degree 1. And so these are all like your slope-intercept form equations. And so in general, they're just a straight line like this. Quadratic functions are degree 2. And so that is when you have a parabola. Parabolas will either be upward facing like this, or if it has a negative leading coefficient, then it would be upside down and make an N shape. When we have a polynomial function of degree 3, then we have a cubic function. When it's degree 4, then we have a quartic function. And when it is of degree 5, we have a quintic function. So anything over than that, for the sake of this course, we'll just say 6th degree, 7th degree, 8th degree, and so on. But something that I do want to point out to you are the relationship between the degree and how many intercepts we can have for the x-axis. So if we look at the degree of 0, notice how it never crosses the x-axis. So it has 0 x-intercepts. When we have a degree of 1, it touches the x-axis once. So we could have 1 x-intercept. With a quadratic function, you'll notice that it is crossing the x-axis twice. And we have 2 x-intercepts here. For degree 3, we have 1, 2, 3 x-intercepts. For degree 4, we have 1, 2, 3, 4 x-intercepts. And for degree 5, we have 1, 2, 3, 4, 5 x-intercepts. Whatever the degree of the function is, that is the maximum number of x-intercepts you could have. So if we had a 6th degree function, it could not have 7 x-intercepts. The degree is the maximum amount of x-intercepts that you will have. So now let's look at end behavior. And remember, you learned about end behavior in Algebra 1. And we're just going to kind of refresh your memory here for a minute. For this first example right here, we have y equals, or f of x equals x squared. So this is a quadratic function. And here it's saying the degree is even, and that's because the highest degree that we have is 2. 2 is an even number. The leading coefficient is positive. Leading coefficient means when your function is written in standard form, the coefficient of the first term is positive. So leading is the first term, coefficient is the coefficient of that first term, so the number in front of the variable. Here we only have one term, x squared. The coefficient here is 1, so that's where the positive comes from, because 1 is a positive number. So whenever you have a degree that's even and the leading coefficient is positive, your end behavior is always going to look the same. And if we look up here at our even functions, 2 is even and 4 is even. If you look at the ends of the graph, both sides are pointing up, both sides are pointing up. So whenever it is an even degree and the leading coefficient is positive, your end behavior will always be going the same way. So here, as x, remember this arrow means approaches. So as x approaches negative infinity, this is saying look at where your x values are negative. Your x values are negative on the left side. The left side of your graph is pointing up. If it's pointing up, then your y values, or in this case your f of x values, are heading to positive infinity. Down here, as x approaches positive infinity, so this is telling you to look where your x values are positive. your x values are positive on the right side of your graph. So on the right side of your graph, that's over here, your graph is pointing up. So that is heading to positive infinity. This will be your end behavior whenever your degree is even and your leading coefficient is positive. Now, what happens if you have a degree that is odd? Well, that's like this one right here where we have f of x equals x cubed. Here, my degree is odd. My leading coefficient is 1. 1 is a positive number. If we look at our end behavior, the first side is down, the left side is down, and the right side is up. Let's look at our odd functions over here. So my odd functions, let me use a different color, are linear, cubic, and quintic. Left side is down, right side is up. So it doesn't matter, but if your degree is odd and your leading coefficient is positive, then your end behavior is always going to look like this. So let's see what this one looks like. As x approaches negative infinity, this is again telling you to look at the left side of your graph. If it helps, this is the left side, this is the right side. The left side of my graph is pointing down. If it's pointing down, that's telling me it's going to negative infinity. As x approaches positive infinity, this is telling me to look at the right side of my graph. The right side of my graph is pointing up, so that is going to positive infinity. What happens when your leading coefficient is negative? So on these two, everything is the same, except here my leading coefficient was positive 1, and now on this one my leading coefficient is negative 1. So the only difference here, excuse me, is that my leading coefficient is negative. So notice, instead of my graph being U-shaped, now this graph is N-shaped. So as x approaches negative infinity, that's telling me to look at the left side of my graph. The left side of my graph is pointing down, so that is going to negative infinity. As x approaches positive infinity, that's telling me to look at the right side of my graph. The right side of my graph is pointing down. That is going to negative infinity. Something that I want to point out to you, whenever your degree is even, either both sides go up if your leading coefficient is positive, or both sides go down if your leading coefficient is negative. When we look at our odds, they are going in opposite directions. So with your end behavior, if your function is even, then where your y values are going should be the same. And if your function is odd, then they're going to be the opposite. So let's see how that works with this bottom one over here. Again here, our degree is odd, just like how it was right above it. But now our leading coefficient is negative. So this one's going the opposite direction as this one. Kind of like thinking about like a linear equation, right? If I had a linear equation with a positive slope, I would be going up from left to right. And if I had a linear equation with negative slope, I would be going down from left to right. And if you notice, even though these graphs are cubic, the end behaviors are the same. So let's look at the end behavior of this last one. As x approaches negative infinity, that is telling me to look at the left side of my graph. The left side of my graph is pointing up, so that is going to positive infinity. As x approaches positive infinity, that's telling me to look at the right side of my graph. The right side of my graph is pointing down. That is going to negative infinity. Down here it says to sketch the general shape of each function. So you don't need to have a coordinate plane or a graph. It just wants to know in general, what does this look like? When I look at example 1, I notice that my degree is 2. That's quadratic. My leading coefficient is positive, so that means it's going to be U-shaped. So my graph would look like this in general. So it just wants a general shape. What is the idea? What if I were to graph this using Desmos, or if I had a coordinate plane, what shape am I looking for? And that's all you're drawing, is the general shape. When you're doing these, you want to look for your degree and you want to look for the leading coefficient. The degree tells you the shape, and the leading coefficient tells you which way it's going to go. So the direction. So if I had a cubic function, like how I have on example 2, this one's cubic because my highest degree is 3, and it's negative. So I know it's going to, because it's odd, I know it's going to kind of look like a linear function, but I know it has at most 3 x-intercepts. So a negative linear function goes down from left to right. And so this one will as well. And then I'll have 1, 2, 3 x-intercepts. And if this is like completely blowing your mind as how you're thinking about this, you could go ahead and you could use a tool like Desmos. Go to desmos.com. Let me get on Wi-Fi here. If you go to desmos.com and you click on the graphing calculator, you can just type in the function. We are looking at negative x cubed plus 5. So I'm just going to type in negative x cubed plus 5. And that's the general shape. Starts up tall, has a little bump in the road, and goes down. And if we look at what I drew, same idea. We're just getting the general shape. It doesn't have to be perfect. If you zoom in on Desmos, it gives you more of an idea of what it's going to look like. So on example 3, we have negative x to the 4th plus 6x cubed minus 3x squared minus x plus 5. The only thing that you really care about is the highest degree, which is 4, and that it's negative. If you look up here, your degree of 4 makes a W shape. If it's negative, it's going to be upside down and make an M shape. And so in general, this one would look like this. That's all that it's asking you to do, is just sketch the idea that you'd be looking for if you were to graph this. Because if I were to graph this function and I were to get a line, then that would tell me, oh wait, that's a red flag. I know this is not supposed to be a line. It's quartic, so it's got to either be an M shape or a W shape. If we look down here at example 4, it says describe the end behavior, left end, right end, of each function using rises and falls. So instead of using the end behavior notation that we typically use for functions, here, instead of saying, this is going to negative infinity and this would go to negative infinity, it's pointing down, so I would just say the left side falls, the right side falls. Or here I would say the left side rises because it points up, and the right side falls because it points down. So it's the same idea, just using different words. So if you're not sure what this graph looks like, you could graph it in Desmos just by typing it in and looking at it. Or you can say, okay, I know that it's a negative coefficient or a leading coefficient, and your highest exponent is odd. So in general, the end behavior would look like a line with negative slope. So I want to know what the left side does, and I want to know what the right side does. Well, the left side would be pointing up. Pointing up means that it rises. And then the right side is pointing down, so the right side falls. And that's the whole idea that we're doing here. If I pull back up Desmos, you could go ahead and type that in. It's another cubic. So again, the right side up here is going up, so that the left side is going up, so that rises. The right side is going down, so that falls. On example 5, we have a positive leading coefficient, and then my degree is 5. So it's positive and it's odd. So this would look like a line with positive slope. So again, I want to figure out what the left side is doing and what the right side is doing. Same thing over here. Left side, right side. So the left side is going down, so the left side falls. The right side is going up, so the right side rises. And if you weren't sure, you could graph that in Desmos and look at your left side and your right side. On example 6, I have a leading coefficient that is positive, and I have the highest exponent of 2. So I know this is going to be an upward facing parabola. So the left side is pointing up, so the left side rises. The right side is pointing up, so the right side rises. And that's all that it's asking you for here. And then when these last 3 problems, it says write the end behavior of each function as x approaches negative infinity and as x approaches positive infinity. So this is using the notation that we used on that first page. So my notation for all of these is going to be the same. So I'm going to go ahead and write them out for all 3. As x approaches negative infinity, I want to figure out what y is doing, or in this case, what f of x is doing. And as x approaches positive infinity, I want to figure out what f of x is doing. And I'm going to go ahead and write that out for these 2 over here as well. So as x approaches negative infinity, I want to figure out what g of x is doing. And again, I'm just using whatever function they gave me here. If they gave me h of x, I would write h of x. If they gave me y, I would write y. Whatever's here goes in this spot. And as x approaches positive infinity, I want to figure out what g of x is doing. And on this last one, as h of x, whoops, not there yet. As x approaches negative infinity, I want to figure out what h of x is doing. And as x approaches positive infinity, I want to figure out what h of x is doing. So on example 7, my leading coefficient is positive 1, and my highest exponent is 3. 3 is an odd number, and so a positive function that's odd is going to look like a line with positive slope. As x approaches negative infinity, this is telling you to look at the left side of your graph because that is where your negative x values are. The left side of this graph is pointing down, so that's going to negative infinity. As x approaches positive infinity, that's telling you to look at the right side of the graph. The right side of the graph is going to be pointing up, and so that would be going to positive infinity. If this part right here, you're like, how are you getting that this is going to be what the end behavior is like? Just go ahead and graph this in Desmos and get it from there. On example 8, we have g of x equals x to the 5th minus 3x cubed plus x. Again, the only things we really care about are the leading coefficient and the degree. My leading coefficient is positive 1, and my highest degree is 5. So again, this is an odd function that's positive, so my end behavior is going to be like that of a line with positive slope. So as x approaches negative infinity, well, that's telling me to look at the left side of my graph. The left side of my graph is pointing down, so that's going to negative infinity. And as x approaches positive infinity, I want to look at the right side of my graph. The right side of my graph is pointing up, so that's going to positive infinity. And lastly, on example 9, as x approaches negative infinity, well, let's see. I have a leading coefficient of negative 1, and my degree is 4, so this will have an end behavior like, so it's even, so it's going to be like a parabola, and then it's negative, so it's going to be upside down, so a downward facing parabola. Now we know that a quartic function would really be like an m, but the end behavior is going to be the same. So as x approaches negative infinity, that's telling me to look at the left side. The left side of my graph is pointing down, so that's going to negative infinity. And then as x approaches positive infinity, that's telling me to look at the right side of my graph. The right side of my graph is pointing down, so that is going to negative infinity.